Welcome everybody. It's week 2 of our friendly introduction to abstract algebra, and we are looking at the solutions to problem set number 2. Here you have it. The first exercise is as trivial as it sounds. You're supposed to write down the elements of D2, which is the symmetry group of a regular two-gon, meaning nothing but a straight line with two vertices. And then show that this is nothing but S2, the symmetric group on a set of two elements. Okay, here we have the regular two-gon, and of course there is the identity, which does nothing to this object. So in permutation notation we have 1, 2, and they stay where they are. So here in the second row we also have 1, 2. This is the identity. Then we have another symmetry, which is rotation around the middle by 180 degrees, or we might as well flip the two-gon around this or about this axis, or reflect it about this axis, so that the two vertices get interchanged. This symmetry I call R, so the corresponding permutation row would be 1 goes to 2, 2 goes to 1. So we have this here, and obviously those are all. There are no more symmetries of the regular two-gon. So the dihedral group D2 consists of nothing but the identity and R. And this corresponds here to these two permutations, and we see, well, this is nothing but S2, because there are only two elements in S2, namely the identity and here the permutation that just interchanges 1 and 2, and that's it. There are no more bijective maps from the set 1, 2 into it or onto itself. So this is it. D2 is obviously the same, except for notation as S2. We shortly talked about the concept of isomorphism. It is not enough that the sets are the same or have the same number of elements, but we want this map here that sends the identity to this identity. Could have used two different symbols here, but that is not really necessary. So this map here sends the identity to this identity and the rotation R to the permutation rho. And we want this map to preserve the composition, because remember, we have groups here. We can use the composition of these elements, which gives me a binary operation on this set, which transforms this set, this mere set, into a group. And with the identity I have no problems, of course. So the only thing I have to check is that rho composed with itself, which is nothing but rho squared. This gives me the identity, of course, because if I apply rho and then rho another time, I end up with the two-gon I started with. And you have to check that this actually is the same as taking the image of R composed with R. Then this map here is composition preserving. And this, of course, is true because R composed with R is the identity, and if I map that, I end up with the identity here. If this sounds a bit cryptic to you or you didn't understand it, do not worry. We will talk about the concept of isomorphism in detail in some weeks. Okay, that's it for exercise number 1. In exercise number 2, we study the symmetric group on 3 elements, namely on the set 1, 2, 3, in detail. First of all, we must write down all the elements of this permutation group and find their inverses, and then we have to do some explicit calculations to get used to calculate with permutations. So let's do this. First of all, S sub 3 consists of 6 elements. Y, or here written as 3 factorial, 3 times 2 times 1, y. We have to map these numbers bijectively onto themselves. So for the first number, I have here 3 possibilities. I could write 1, 2, or 3 here. For the second number, there remain only two possibilities, because I can have the same number here. Like for example, here 1 and here 1, this would not be bijective. So only two possibilities remain. And for the third number, there is only one possibility left if I want to have a bijective map. So all in all, we have 3 times 2 times 1, making 6 elements. And here they are. Now it is not necessary but very helpful to have a geometric picture in mind, because remember, S3 is nothing but D3, the dihedral group of an equilateral triangle in another costume. So here, of course, we have the identity. This here corresponds to rotating the triangle by 120 degrees. Vertex 1 goes to where vertex 2 was, vertex 2 goes to vertex, or number 2 goes to where vertex 3 sits, and so on. This here then is the rotation by 240 degrees, and these 3 elements are the reflections, because you see here one vertex here, here and here stays the same, and the other 2 get flipped around or interchanged. So these here are all the 6 possible bijective maps from the set 1, 2, 3 onto itself. So these are all the elements of S3. Next, we are supposed to find all the inverse elements, because remember, in a group, every element has to have an inverse element that nullifies its action. So as we learned in the corresponding video, if I want to find the inverse of this rotation permutation here, I read it from bottom to top. So 1 goes to 3, so I put a 3 here. 2 goes to 1, so I put a 1 here. And then here must be a 2, because I want to have a bijective map. And if you look at that, this is nothing but row sub 2, or the rotation by 240 degrees. Vertex 1 goes to where vertex 3 was. I have the rotation by 240 degrees. And then, of course, the inverse of this here is nothing but row itself, or row sub 1. So row 2 inverse is row 1. And with the geometric picture in the back of your mind, this is very obvious, because if I rotate by 120 degrees and then by 240 degrees, I end up with the same triangle I started with, because I have rotated by an angle of 360 degrees. And this is what is the geometrical background of this result here. So now for the reflections, a sigma or a sigma 1, which is the reflection about the symmetry line that goes through vertex number 1. We read from bottom to top. 1 stays where it is. 2 goes to 3, and then here I must have the 2, and this is sigma itself, which is not surprising, because if I apply sigma and then sigma again, which is abbreviated by sigma squared, I get, of course, the identity, because if I flip the triangle and flip it again about the same axis, I end up with the triangle I started with. So, and this here just means that this guy is the inverse element of that guy, because if I compose them, I end up with the identity. Okay, and this, of course, is true for all the reflections. So, the inverse element of the identity is, of course, the identity. And then the inverse of the rotation by 120 degrees is the rotation by 240 degrees, and in the permutation representation, this is this permutation here. Then, as explained before, the inverse of row 2 is row 1, and then all the reflections are so-called self-inverse elements, because they are their own inverse. This is this relation here. Okay, now for part C, we are supposed to do some concrete calculations. So we define row 1 simply as row, so just that we don't have to write the indices all the time. This here is row, and sigma 1 is defined as sigma. This here means that guy that is here is defined as the object that is here on the other side of the equal sign. That's the meaning of this double point here. And sigma 2, the reflection about symmetry axis 2, is abbreviated by sigma prime. So, and we are supposed to compute all these compositions, where row squared is an abbreviation for row composed with itself. Okay, let's do it. Remember, we read from right to left. In this case, of course, it doesn't matter because row and row is the same, but we read from right to left. We start with the one here. Observe that it is sent to 2, and then we look what happens with the vertex 2 here. It goes to number 3. So 1 goes to 3. Same with 2, 2 goes to 3, 3 goes to 1. So in the composition 2 goes to 1. And then of course we must have the 2 here, but let's check it. 3 goes to 1, 1 goes to 2. Alright. And this here is nothing but row 2, which geometrically makes total sense, because this here means rotate by 120 degrees and then by another 120 degrees. Then of course we end up with the rotation by 240 degrees. If you just look at the numbers here, this is not clear at all. So here it helps to have this geometric background. So next, row to the third power, which is defined as row squared composed with row. We do the same thing again. 1 goes to 2, 2 goes to 1, so 1 stays where it is. 2 goes to 3, 3 goes to 2. Oh, so 2 stays where it is, and 3 goes to 1, 1 goes to 3, 3 stays where it is. And this is the identity, which again geometrically is clear, because here we rotate by 120 degrees followed by a rotation by 240 degrees. This is of course the identity. Rotating by 360 degrees does nothing to the triangle. Okay, now a bit faster. Sigma squared, we observed this before in part B, is the identity. Sigma composed with sigma prime. This is a bit interesting. If you compose two reflections, you end up with a rotation. I would encourage you to think about this in your mind, or just cut out a triangle and then flip it about the corresponding axes, and you'll see you'll end up with the same result as if you had rotated the triangle by 120 degrees. And if I interchange here the order, sigma prime, and before that sigma, I end up with another rotation, the rotation by 240 degrees. So here we see S3 is a non-commutative group, because the order of composition is important. We do not get the same result here. Then we are supposed to calculate this composition here. First a sigma, then rho, then a sigma again. You just write it down and do the same number chasing as we did above. 1 goes to 1, 1 goes to 2, 2 goes to 3, so all in all 1 goes to 3. 2 goes to 3, 3 to 1, 1 to 1, so 2 goes to 1, and then we are left with a 2 here. And this is actually the rotation by 240 degrees, or rho squared, which is the same as the inverse of rho. If you're a good geometric thinker, try to visualize it in your mind. You flip the triangle, you rotate it by 120 degrees, and you flip it about the same axis, and then it's the same result as if you had rotated it by 240 degrees, or reversed the rotation by 120 degrees. And to end part C, we are supposed to show that this here is the same as this relation here. Now, of course, we could do this by brute force again, just write down both sides and see, oh, it's the same permutation. But we're going to do it a bit different because we have to get used to the abstract reasoning in groups, which we are going to do in the next weeks. We already have established this relation here. Now I compose both sides with sigma from the right. Then, of course, the result here must be the same, because composing with an element leads to a unique new element. And if those two guys here were the same, then their composition with this element sigma must also be the same. Otherwise, the composition would not be well defined. So here we have this, and now is the first time that we actually use associativity of composition, meaning we can drop these parentheses here, because associativity tells us it's not important in which order we compose, in the sense that we could do this, then that, or we could compose here first and then with that. So just dropping the parentheses gives me sigma, rho, sigma composed with sigma, which is nothing but sigma squared. But sigma squared is the identity, because I have flipped 2 times. So on this side here, we are left with sigma composed with rho, and on the other side, we are left with rho inverse composed with sigma, which was to be shown. This here you could call an anti-commutation relation. I cannot commute sigma and rho. If I try to, I have to write the inverse of rho here. So again, this is another example that this group is non-commutative. Now for the last part of this exercise number 2, you are to show that S3 can be written as this set here. The powers of rho composed with the powers of sigma, where the exponent here of rho runs from 0 to 2, and the exponent of sigma, it can be either 0 or 1. Why? Well, if we have sigma squared, this is nothing but the identity, so we repeat ourselves, and here the same. Rho to the 3rd power is the identity, so we can stop after 2. And for any group element, g to the power of 0 is simply defined as the identity. Okay, and we do this by brute force. We simply write down all the elements of the set on the right-hand side, so all the powers of rho composed with all the powers of sigma, and here, of course, we get the identity. Rho to the 1st power composed with sigma to the 0th power, which is nothing but the identity is rho, of course. Then here we get rho squared, which is nothing but rho sub 2. Then here we end up with sigma 1. Now rho composed with sigma both to the 1st power gives me sigma 3, the reflection about symmetry axis number 3. And rho squared composed with sigma gives me sigma 2. If you're a beginner, it's very worthwhile to do these calculations, or at least check that they are correct. I'm skipping those now. And so I see all these compositions here give me all the 6 different elements of S3, so we are done. S3 can also be written as these elements here. Now a short notation for that is we call rho and sigma the generators of this group and write the group S3 is rho sigma, and then we have these brackets here, meaning exactly this here. You take all the powers of rho and compose it with all the powers of sigma, and then you end up with the whole group S sub 3. And now, since we know that there is this nice one-to-one correspondence between S3 and D3, the dihedral group of the equilateral triangle, we immediately see that also the group D3 is generated by two elements, namely the corresponding symmetries. So here the rotation by 120 degrees and the reflection doesn't actually matter about which axis you reflect. Okay, last exercise in problem set number 2. We are looking at the permutation representation of D4, the dihedral group of a square, a regular fourgon, and do essentially the same as here in exercise number 2. So first of all, we are supposed to write down all the elements of this group of permutations as well as their inverses. So as we did last week, we choose the following notation. Here, counterclockwise, the vertices of the square are numbered 1, 2, 3, 4. Then here is the center of mass, and this symmetry axis I call axis number 1, and then I move always about 45 degrees to obtain axis 2, axis 3, and axis 4. Rho 1, which is abbreviated by rho, is the rotation about or by 90 degrees of this rectangle here, of this square. And then, of course, 1 goes to 2, 2 goes to 3, 3 goes to 4, and 4 goes to 1. Then rotating by 180 degrees, which is nothing but applying rho twice, so rho squared. 1 goes to 3, 2 goes to 4, 3 to 1, and 4 to 2. And then rho to the third power is the same as rotating by 270 degrees, and then we get this permutation here. Then I have the reflections about these symmetry axes. Sigma 1 is reflecting the square about this axis, so 1 goes to 4, 2 goes to 3, and 3 goes to 2, and 4 to 1. And then the same for all the other axes. We end up with sigma 4, which is reflecting about this axis here. And here we have 2 and 4 are fixed, and 1 and 3 get interchanged. So we have 4 reflections and 3 rotations. Did we forget an element? Not really, because here the fourth power of rho is simply the identity, and we always have the identity as a permutation. So, and the inverses are also pretty clear. The inverse of rotating by 90 degrees is rotating by 270 degrees, or applying rho 3 times. The inverse of rotating by 180 degrees is itself rotating by another 180 degrees, and here the inverse of rho to the third power is simply rho. And of course all the reflections are self-inverses. If I apply them twice, I end up with the identity, so this here is very easy. So in part B, remember we had a nice one-to-one relation between D3 and S3. Maybe there is something similar with this permutation group and the symmetric group on 4 elements. Unfortunately, there is not, because D4 contains only 8 elements, as we have seen before, but the symmetric group on 4 elements contains 24 elements. Why? Because think of them again as bijective maps from this set into itself, For the first number you have 4 possible choices. For the second number only 3, because you have to be bijective. For the third number only 2. For the last number you have no more choices. So we get 4 times 3 times 2 times 1 possibilities, or for short 4 factorial, which is 24. So of course there cannot be a one-to-one or bijective correspondence between a set with 8 elements and a set with 24 elements. The geometric reason is that not every permutation gives rise to a symmetry of the square. Take a look at this permutation here. This is clearly a bijective map. Just shuffles these 4 numbers around. But it cannot correspond to a symmetry of the square. Why? Because 1 is the only vertex that stays fixed, and the only symmetry that achieves that, besides the identity of course, but this pi is obviously not the identity, would be the reflection about axis 2. But then 3 has to stay in its position, which it does not in the permutation pi. So this permutation pi here cannot correspond to a symmetry of the square. Pi, of course, doesn't mean the circle number, but is a well-liked symbol for a permutation because it's a small p in Greek, pi. Okay, now the last part. You're supposed to adapt parts C and D of the above exercise to the group D4 in permutation representation. Okay, here I'm a bit lazy. If you're really a beginner and new to all of this, then please do some more explicit calculations. For example, consider here the generated set by these 2 elements, meaning you take all the powers of rho and compose it with all the powers of sigma. Here k runs between 0 and 3 because rho to the 4th power is the identity, and again L, the exponent of sigma, runs or is just 0 or 1 because sigma squared is the identity. Write down some of those, do the explicit calculations, and find out you end up with exactly 8 different elements, which are nothing but the elements of D4 in permutation representation. Okay, that's it for this week. I hope the solutions were helpful. As always, please like and subscribe and leave a comment. If you're already familiar with groups, this of course was all trivial stuff. But as I said before and will repeat many times, this is really aimed at beginners who are really new to the subject. And for them, I think those were some really neat exercises to get used to calculating with permutations and learn some new concepts, like for example the group generated by 2 elements. All right, I hope you tune in next week, and I'm looking forward to it. Bye bye.